basically, quantum noise and quantum errors can reduce entanglement fidelities and can reduce entanglement generation rates. So we really want to try to avoid these errors and noise as much as we possibly can. But on some level, the noise and errors are unavoidable. These quantum noise and errors will come from basically the environment acting on the qubit, and the qubits are extremely sensitive to temperature, vibration, if it's a solid state qubit, inhomogeneities in the material, basically pretty much anything you can think of can disturb a qubit. So on the next couple of slides, we'll look at kind of ways we can classify some of the noise that happens on stationary qubits. We'll look at specifically dephasing noise, bit flip noise, depolarizing noise, and amplitude damping noise. And then we'll also shift to looking at photonic qubits and types of noise that can occur for them. So we'll specifically be looking at just the loss of the photon as our noise example, but there are other types of noise that can occur as well for photonic qubits. So in order to talk more about the types of noise that affect stationary qubits, it's useful to kind of go back to some of the quantum basics and talk about something known as the Bloch sphere. The Bloch sphere is one way people use to represent qubits. Basically, it's a sphere with a radius of 1, and the top of the z-axis, and with a center at, say, like the origin of a Cartesian coordinate system. The top of the z-axis for this Bloch sphere will represent the 0 quantum state, and the bottom of the z-axis will represent the 1 quantum state. And now it's actually possible to represent any quantum state on this Bloch sphere as just a vector, which points in any direction on the Bloch sphere. So, for instance, if we look at a quantum state where we have a 50% chance of measuring 0 and a 50% chance of measuring 1, this would be a quantum state lying somewhere on the xy plane. In particular, the x and y axis will represent different superposition states with different phase. So phase in this context tells you basically where on the Bloch sphere you are. To get a more physical sense of what it will mean, of course, in classical waves, a phase will tell you where along one period of a wave you are. In quantum mechanics, phase tells you something kind of similar. Although it can't be directly observed, it will add dimensionality to the qubit. And this dimensionality basically affects the state of the qubit. And now that we understand the Bloch sphere, we can understand how bit flip errors work on qubits. So bit flip errors are a good place to start because they have a really intuitive analog in classical computing. Basically, a bit flip error in a classical computer is just when a 0 becomes a 1 or a 1 becomes a 0. So in the quantum world, the bit flip error is very similar. And if we recall that our 0 is at the top, is at kind of the top of the z-axis, and our 1 state is at the bottom of the z-axis, we can see that what a bit flip error will actually do quantum mechanically is it will correspond to a 180-degree rotation on the Bloch sphere. So I started out in my 0 state, I wanted to stay in my 0 state, but I experienced a bit flip error and I end up in the 1 state. The great thing about this definition is that it allows us to also define bit flip errors for states where it might not be so obvious kind of what this would intuitively correspond to. So if we start in, say, a superposition state, say we start pointing along the y direction of this Bloch sphere, meaning that we have a 50% chance of measuring 0 and a 50% chance of measuring 1. Our bit flip error will still correspond to a 180-degree rotation, but it will bring us back along the XY plane, but just in a different direction. So our phase will change, but we will still have a 50% chance of measuring 0 and a 50% chance of measuring 1. So another type of error which can happen in quantum systems are dephasing errors. So for this type of error, we can look at one example where we start out in the superposition state. So we start out in with our qubit corresponding to a 50% chance of measuring 0 and a 50% chance of measuring 1. And over what happens with the dephasing error is that over time, the phase becomes less known and less well defined. So what this will correspond to on the Bloch sphere is the kind of direction of the arrow becoming less known. So in this picture, I've drawn a bunch of arrows, but that doesn't mean that we're getting a bunch of new qubits or anything. We still have one qubit. We just don't know exactly where it's pointing anymore on this XY plane. So, however, for this dephasing errors, if you start out in the 0 state, you'll still remain in the 0 state, and the dephasing error will not affect it. So we also have depolarizing errors. In this type of error, you can begin, say we could begin in the 0 state, and if our qubit experiences a depolarizing error, it has some probability of basically becoming a completely mixed state. So this means that it could kind of lie anywhere on the Bloch sphere. And again, I've kind of represented this as just a bunch of arrows drawn anywhere on this Bloch sphere. Similarly, it doesn't, for this error, it doesn't matter where your what state you start in, you'll still end up with this completely mixed state. So there's also amplitude damping errors. For these types of errors, you could begin in, say, the 1 state, and you'll always return back to the 0 state. So if you begin in the 0 state, you'll stay in the 0 state. If you begin in the 1 state, over time, you'll return back to the 0 state. And if you begin basically anywhere in the Bloch sphere, over time, you'll return back to the 0 state. Now that we've kind of introduced some different types of quantum noise, we can talk about one way people use commonly to avoid one of these types of noise, or to kind of extend basically the time before the qubit is destroyed by this type of noise. In particular, we'll be talking about dephasing noise and dynamical decoupling. So again, dephasing noise was this type of noise where the qubit's phase becomes undefined over time. Dynamical decoupling is actually a technique which can help with dephasing noise and kind of help undo the effects of it. So what happens is we can look at this graphic on the right, which shows a Bloch sphere. In this graphic, it begins with the state in the 0 state, and then it rotates down to be a superposition state. And over time, the qubit experiences dephasing noise, where you can see that the single arrow becomes a bunch of arrows that are kind of spread out. And some of these arrows are traveling more quickly than others. But what you can actually do to kind of fix this noise is you can actually do a bit flip operation. So we talked about bit flip errors corresponding to 180-degree rotations on the Bloch sphere. If you intentionally perform a bit flip, then it's no longer an error, it's just an operation. So you can do a bit flip operation, which will then cause all of the kind of errors that were traveling more quickly in one direction to now travel more quickly in the other direction, and now the qubit will kind of rephase. This is known as a spin echo technique, and it's one type of dynamical decoupling and one way people will extend the lifetime of qubits.